When upgrading a 400 amp 277/480 volt circuit, there are several factors to consider when selecting the appropriate conductors. Given the existing infrastructure and the desire to reduce stress in the existing equipment, you're exploring options to run parallel conductors from a second main distribution panel. Let's analyze the options of using 3/0 copper conductors versus 4/0 aluminum or 250 kc male aluminum conductors per phase. Firstly, let's examine the option of running 3/0 copper per phase. The advantages of using copper are that copper is a good conductor with excellent current carrying capacity. Also, smaller wire size compared to aluminum makes it easier to pull. However, the disadvantages are that copper is more expensive than aluminum, and it also requires 12 conductors, that is 4 phases and 4 neutrals, in parallel. Now, let's examine the option of running 4/0 aluminum or 250 kc male aluminum per phase. The advantages of aluminum are that aluminum is a lightweight and economical conductor, and it requires fewer conductors, that is 8 conductors for 4/0 aluminum and 6 conductors for 250 kc male aluminum. The disadvantages are that larger wire size compared to copper can be more difficult to pull. Also, aluminum is more susceptible to oxidation and corrosion. Considering the available space and the ease of pulling the conductors, running 3/0 copper per phase is a viable option. Now let's discuss some additional considerations. When splicing conductors, consider using mechanical splicing connectors or heat shrink tubes to connect the parallel conductors. Run the same number of neutral conductors as phase conductors. Install an additional ground conductor size according to the National Electrical Code. Use pull boxes to divide the run into smaller sections for easier pulling. Use wireway as much as possible to avoid pulling through conduit. Clearly label the conductors and ensure proper termination at both ends. Selecting the right conductor size involves calculating the ampacity required for the load. For a 400 amp circuit, you need to ensure that the conductors can safely handle the current. According to the National Electrical Code Table 310.15b16, which is now Table 310.16, the ampacity of conductors depends on their size, insulation type, and the ambient temperature. For copper conductors with THHN insulation, a 3/0 conductor has an ampacity of around 200 amps at 75 degrees Celsius. Since you're running parallel conductors, you'll need at least 2 3/0 copper conductors per phase to meet the 400 amp requirement. For aluminum conductors, a 4/0 conductor has an ampacity of around 180 amps at 75 degrees Celsius. A 250 kc mil aluminum conductor has an ampacity of around 215 amps at 75 degrees Celsius. Similar to the copper option, you'll need to run multiple aluminum conductors in parallel to meet the 400 amp requirement. When using parallel conductors, it's crucial to ensure that they are the same length, material, size, and insulation type. This ensures that the current is evenly distributed among the conductors. According to the National Electrical Code Section 310.10h, parallel conductors must be sized no smaller than 1/0 for sizes 1/0 and larger. The National Electrical Code also requires that you adjust the ampacity of the conductors based on the number of current-carrying conductors in a raceway or cable. This is known as ampacity adjustment. When you have more than 3 current-carrying conductors in a raceway, you need to reduce the ampacity of each conductor to account for the increased heat generated by the conductors. The adjustment factors are provided in the National Electrical Code Table 310.15 code, which is now Table 310.15b3r. For example, if you have 4 to 6 current-carrying conductors in a raceway, you need to reduce the ampacity of each conductor by 80%. This means that if the unadjusted ampacity of a conductor is 200 amps, the adjusted ampacity would be 160 amps. Therefore, you need to select conductors that have an ampacity that is higher than the load current after applying the adjustment factors. Given that you have installed 10x10 wireway to eliminate pulling through pipe, this can help simplify the installation. Wireways provide a more open space for running and managing conductors, which can reduce the pulling tension and make it easier to install the conductors. However, you still need to consider the fill capacity of the wireway to ensure that you don't exceed the maximum allowable fill. According to the National Electrical Code Section 376.22, the sum of the cross-sectional area of all conductors in a wireway must not exceed 20% of the interior cross-sectional area of the wireway. This is to ensure that there is enough space for ventilation and to prevent overheating of the conductors. When using pull boxes to interrupt the length of the run, it's important to size the pull boxes correctly. The National Electrical Code Section 314.28 provides guidelines for sizing pull boxes and junction boxes. The size of the pull box depends on the size of the raceways entering and exiting the box, as well as the number of conductors and the angle of the pull. For straight pulls, the length of the pull box must not be less than 8 times the trade diameter of the largest raceway entering the box. For angle pulls, the distance between each raceway entry inside the box and the opposite wall of the box must not be less than 6 times the trade diameter of the largest raceway, plus the sum of the diameters of all other raceways in the same wall. You also need to consider the bending radius of the conductors when making bends inside the pull box. The National Electrical Code Section 300.34 requires that the bending radius of conductors be large enough to prevent damage to the conductor insulation. The minimum bending radius depends on the size of the conductor and the type of insulation. When making connections in the pull boxes, it's important to use the appropriate connectors for the type and size of the conductors. For copper conductors, you can use compression connectors, mechanical connectors, or set screw connectors. For aluminum conductors, you should use connectors that are specifically designed for use with aluminum conductors. These connectors are typically made of aluminum and are designed to provide a gas-tight connection to prevent oxidation and corrosion of the aluminum conductors. When using aluminum conductors, it's also important to use an antioxidant compound in the conductors before making the connection. This compound helps to prevent oxidation of the aluminum and ensures a good electrical connection. The antioxidant compound should be applied to the conductor strands before inserting them into the connector. When terminating the conductors at the main distribution panels, it's important to ensure that the terminals are properly rated for the size and type of conductors being used. The terminal should also be tightened to the manufacturer's specified torque to ensure a good electrical connection. Over-tightening the terminals can damage the conductors or the terminals, while under-tightening the terminals can result in a loose connection and overheating. It's also important to label the conductors clearly at both ends to identify the circuit and the phase. This helps to prevent confusion during maintenance and troubleshooting. The labels should be durable and resistant to fading or smudging. When installing the ground conductor, it's important to size it according to the National Electrical Code Table 250.122. The size of the ground conductor depends on the size of the ungrounded conductors. For example, if the ungrounded conductors are 3/0 copper, the ground conductor should be no smaller than number 8 copper. The ground conductor should be connected to the equipment grounding bus in the main distribution panel and to the metal enclosure of the equipment being served. It's also important to ensure that the ground conductor is properly bonded to the metal raceway or cable tray system. This helps to provide a low impedance path for fault current to flow back to the source, which is necessary for proper operation of the overcurrent protection devices. When running parallel neutral conductors, it's important to ensure that they are the same size and material as the phase conductors. The neutral conductors should also be run in the same raceway or cable as the phase conductors. This helps to minimize the impedance of the neutral conductors and to ensure that the current is evenly distributed among the neutral conductors. In some cases, it may be necessary to increase the size of the neutral conductors to account for harmonic currents. Harmonic currents are non-sinusoidal currents that can be generated by electronic equipment such as computers, variable frequency drives, and electronic lighting ballasts. These harmonic currents can overload the neutral conductors and cause them to overheat. The National Electrical Code Section 220.61 provides guidelines for calculating the neutral load and for determining whether the neutral conductors need to be increased in size. When selecting overcurrent protection devices for the circuit, it's important to choose devices that are properly rated for the voltage, current, and interrupting rating of the circuit. The overcurrent protection devices should also be selected to protect the conductors from overload and short-circuit conditions. The National Electrical Code Section 240.4 provides guidelines for protecting conductors from overcurrent. The overcurrent protection devices should be sized no larger than the ampacity of the conductors being protected. In summary, when upgrading a 400 amp 277/480 volt circuit, it's important to carefully consider the conductor size, material, and installation methods. You also need to ensure that you comply with all applicable requirements of the National Electrical Code. By following these guidelines, you can ensure that the upgraded circuit is safe, reliable, and meets the needs of the electrical system. Remember to consult with a qualified electrical engineer or contractor to ensure that the installation is done correctly and in accordance with all applicable codes and regulations. Proper planning and execution are essential for a successful electrical upgrade. The choice between copper and aluminum conductors depends on various factors, including cost, ampacity, and installation considerations. While copper offers higher conductivity and smaller size for the same ampacity, aluminum is more cost-effective and lighter. However, aluminum requires careful installation practices to prevent oxidation and ensure reliable connections. The selection of overcurrent protection devices, such as circuit breakers or fuses, is crucial for protecting the conductors and equipment from overloads and short circuits. The overcurrent protection devices must be properly sized and rated for the circuit voltage, current, and interrupting capacity. Coordination studies should be performed to ensure that the overcurrent protection devices are coordinated to minimize the extent of any power outages in the event of a fault. Proper grounding is essential for electrical safety. The grounding system provides a low impedance path for fault current to flow back to the source, which allows the overcurrent protection devices to quickly clear the fault. The grounding system must be properly designed and installed in accordance with the National Electrical Code. Regular maintenance and inspection of the electrical system are important for ensuring its continued safe and reliable operation. This includes inspecting conductors, connections, overcurrent protection devices, and grounding systems. Any problems or deficiencies should be corrected promptly to prevent potential hazards. Consider all these factors when upgrading the 400 amp circuit to ensure a safe and reliable electrical system.